This is Module 4, Lesson 1. In this lesson, we'll talk about magnetism. In particular, we'll focus on diamagnetism, paramagnetism, and ferromagnetism. Let's get going. So first, we have to define what is magnetism. Magnetism is typically a magnetic field that's applied to the system. For a typical system, when you have an internal magnetic field that's M, an applied magnetic field that's H, and then your total observed field is actually B. And then we need to detect what is the response of a system to an external magnetic field. And the magnetization curve is the curve that we use to determine the total magnetization of the system. And then the susceptibility is the concept we use to detect the response of a material to an external influence of a magnetic field. At H equals to 0, susceptibility is defined as the derivative of M versus derivative of H. And then when H is linear to M, then we will say susceptibility will be simply M divided by H. So in the case of a paramagnetism, we would have a case in which susceptibility is larger than 0. And in the case of a diamagnetism, we would have a case in which chi is actually less than 0. Let me explain more what that actually means in the next slide. So let us say, what is the definition of diamagnetism? Since we know from our definition of susceptibility that susceptibility is negative for diamagnetic material. So what does that actually mean? Let me give you a very simple example. If you think about typically the gravitational force will force you down on top of the Earth. That's how you stand. But in some cases, say for example, when you have a very light, a simple piece of graphite, and such a simple piece of graphite would actually be able to flow on top of a very strong magnetic field. In addition, if you have a fairly strong external magnetic field, you can actually flow a simple, a live frog inside the external magnetic field. And what is the reason for that? The reason for that is because all materials exhibit what we call the diamagnetism, in which the response is actually in opposite direction as the applied external magnetic field. So what is Lagrangian diamagnetic susceptibility? The diamagnetic susceptibility is actually proportional to a couple of things. Firstly, it's proportional to the number of atoms you have in the system. And then second, it's proportional to the amount of electrons in each of the atoms. And then, of course, it's proportional to the charge of the electron. And then you have mu naught, which is a constant. And then you have the average mean square distance of electron from the nucleus. And then Z is, of course, the number of electrons in each of the atoms. And then for different materials, these are the diamagnetic susceptibility. And how do we actually derive this will be discussed in the light bulb session. Now let me explain the physics of diamagnetism. So we all know what is Lenz's law in electromagnetism class. So let's imagine that we have a simple coil. And let's further imagine we have a magnet. We push this magnet into the coil. As we gradually push the magnet into the coil will actually induce a current which produces a magnetic field in the opposite direction of the force you're trying to push the magnet in. And this is the case when you push it, and this is also the case when you pull it. So what this means is that when you push and pulling the magnet away and into a coil, the coil will produce an instantaneous current that produces a magnetic field that's always in the opposite direction, meaning against the force when you try to push it in. And this is exactly how the electricity is actually produced. So this is actually very important. And diamagnetism actually works in an analogous way, but in the case of the atomic version of Lenz's law instead of a real coil. If you imagine each of the atom is composed of a nucleus and then all the electrons around the nucleus. If you imagine this is sort of like a simple coil around the nucleus, the electrons will be like a simple coil around the nucleus. Then what actually happens is that when you try to push a magnet into it, and it will produce an instantaneous current that produces a field in the opposite direction, just like the Lenz's law is same in the case of how the electricity are produced. So let's think about how in atomic version of Lenz law works. So let's imagine we have Z electrons processed with angular frequency such as this. Of course, the angular frequency is proportional to the external magnetic field you apply. And then it will produce a current. And this current will be proportional to, again, to the external magnetic field, and again, proportional to the number of electrons you have, and then, of course, inversely proportional to the mass you have. In this case, it will be the electron mass. And then the magnetic moment that's been produced by such a current will be proportional to the current, and then it'd be proportional to the area that's been covered by this current. That means you would have a susceptibility that's equals to I multiplied pi and rho squared. And rho squared, of course, is the average, is proportional to the average radius of these electrons. As we said earlier, we will derive this in detail in the light bulb session. With this notion, then we can actually calculate the magnetic susceptibility of a system, which is equals to the magnitude of the magnetic moment and divided by h. And in this case, it will arrive at the equation as this. And then the natural question one wants to ask is that are all materials diamagnetic? If you imagine a system is composed of materials, materials would always have a nucleus and electrons. Unless you have a material only composed of neutrons, then everything that with, at least on Earth, everything with a nucleus and electrons around it, when you push a magnet into it, you will always have a diamagnetic response. Therefore, your diamagnetic response is present in all materials. Then you would ask the question, why would I, typically a person, when I standing near a magnet, I did not get lifted up like a frog gets lifted up, in a strong magnet. And the answer to that question is that the typical diamagnetic response is extremely small. So all the other response, most typically paramagnetic and ferromagnetic response, typically have an order of magnitude or 2 order of magnitude larger than the size of a diamagnetism. And the reason a frog gets floated is because the weight of a frog is much smaller than the weight of a typical person. And in this case, frog, when you have a large enough magnetic field, can actually get floated. So now let me talk about generally what sort of magnetism you can have in nature. Typically, we can have paramagnetism, and this will be the case in which you have actually a local moment surrounding each of the atomic ions, but these atomic ions are not correlated, meaning that your paramagnetic stability will diverge at very low temperature, essentially 0. And then you can have another magnetism, is what we call ferromagnetism. Ferromagnetism is a magnetism in which magnetic order actually forms below a characteristic temperature, which we typically call Tc. And Tc, C here means a Curie temperature. And then we can have a system in which actually magnetic orders antiferromagnetically. A typical or most simple antiferromagnet will be spin up and down, up and down. And in this case, there will not be any net moment, and your stability actually decreases below a characteristic temperature, which we call nil temperature. Of course, you can have a combination of magnetism, both ferro and antiferromagnetic combined, and this case we will call ferrimagnetism. And the stability will be more complicated.